Section 6.4, number 23. We need to solve this big, long equation using identities. And the first identity that jumps out to me will also help this big, giant equation look a lot smaller for us, is that guy. That guy, notice the 5x, 2x of cosines plus 5x and 2x again with sines. So that's repeated. So that jumps out as the difference identity for cosine. So that's 5x minus 2x. Remember, cosine has an opposite sign, same trig functions. So that plus becomes a minus. And the rest, I'm just going to copy down. 1 minus 1 equals 0. And I have cosine of 3x. And the beauty of that subtraction then is that this 5x minus 2x becomes cosine of 3x, which will then combine and be like terms with this cosine of 3x. Still have that minus 1 equals 0. So now I have cosine of 3x plus cosine of 3x is 2 times cosine of 3x. Those are like terms. And I can add 1 to both sides to give me that equals 1, which gives me cosine, dividing both sides by 2, gives me cosine of 3x equals 1/2. Then I can take and leave a little space for my cosine inverse here. So I can take my cosine inverse of both sides, and I get that 3x equals, let's see, 1 is cosine equal to 1/2 pi over 3, or 3x equals 5 pi over 3. Now, my 3x is kind of a big period, so I'm going to have a couple more repeats of this within this range. So even though I want to stay in that range, I'm going to express this in terms of all real numbers, and then we can reduce it to just our given, or I should say our domain, because we're solving for x. So this solution for 3x will be plus any multiple of the period of cosine. And same with this one. Now when I solve for x, so to solve for x, I will divide both sides by 3, and I got to divide each piece by 3 then. So what I get here is x on the left, pi divided by 3 is going to be pi over 9. So I'm going to actually take that a step so you can see how that works. Pi over 3 divided by 3 is the same as times 1/3, which equals pi over 9. Okay. And then that last piece, the 2 pi k divided by 3, gives me plus 2/3 pi over k. But I don't want all reals. I only want when it's going to be between 0 and 2 pi. So if I know k is never going to be negative because our domain starts at 0. But when I plug in a 1, a 2, or a 3 for k, then this total will still be in that 0 to 2 pi. So I get, this is true for k equal to 1, 2, or 3. Actually, not 3, I'm sorry, 0, 1, or 2. 0, 1, or 2. So I plug in 0 for k, I get pi over 9. That's within our range. I plug in 1 for k, then I get k equal to 1 implies, let's actually write it all out. So when k equals 0, I get pi over 9, and then that last term just becomes 0, which equals pi over 9, and that's in our domain. And when I plug in k equals 1, I get pi over 9 plus 2/3. I'm going to put it in terms of 9 as a common denominator, so that's 6 9ths times 2 pi, which is 12 13/9 pi, which is still in our domain of 0 to 2 pi. And when I plug in 2, I get pi over 9 plus 6/9 times 3 pi. Wait a second. What do I want here? 2 pi times 2, which would be 4 pi. Which gives me 6 times 4, 6 times 2 times 2 gives me 24, 25/9. Okay, let me back up here. I think that should just be pi times 1, not 2. Which means that should be 7/9 pi. And this is the one that will be 2 pi, so that one will be 12/13/9. But when I get up to k equals 3, that's when I got to be too big. So I had 19 pi/9, which is too big, not in our range, our domain. So that's why k can be either 0, 1, or 2. And the same thing happens with this other solution. So here's one solution with k equal to 0, 1, or 2. And the same thing happens with this guy over here if you plug in 0, 1, or 2 for those k's. So that's our final solution. Wait a second. Looks like I lost the divided by 3 piece there. Hang on. So this still needs to be divided by 3. Okay, this one. There it is. Sorry, that's our 3x solution. A 3x solution. So this one is x equals 5 pi divided by 9 plus 2/3 pi times k for k equal to 0, 1, or 2. There we go. Yes.